Welcome to the second screencast on trees. Today we'll be discussing binary trees and binary search trees and their implementation. So first off, we have to define what a binary tree node looks like. It implements serializable so that we can use Java to store and retrieve the instances simply. The node has, just like the doubly linked list, has the data. We're making it protected because we want to have access when we subclass the binary tree class. We have a left and a right, just like next and previous. In fact, it looks very similar if you draw it to a doubly linked list, left and right, except for now we're talking about children, not predecessors and successors. The node class has a constructor that allows us to construct it given the data, and the toString method so that we get something interesting, so we just return the data, the toString of the data. The next class is the BinaryTree class. It has a root node, 3 constructors for ease of use, 4 accessor methods that allow us to get the different pieces of the binary tree, and some additional methods for printing out the tree and doing some traversals. So first off, the binary tree implements serializable, again, so that we can store it easily using the Java I/O system. And we have a root node, that is the root of the binary tree. So it's very simple. There's 3 constructors. The first one is the default constructor that sets the root to null. We have another constructor that supplies the root, so we just assign the root to the given root, the node that was passed in. And finally, the third constructor allows us to construct a new binary tree given the root data, the left subtree, and the right subtree. So we assign the root to the data, a new node, and then we assign the left subtree to root.left and the right subtree to root.right. And notice the left subtree is a binary tree, but we're talking nodes, so that's why it's left tree.root and right tree.root, because those are the nodes, and those are the things that we actually point to. So some of the accessor methods, we can get the left subtree of a binary tree. We check to see if the root is null, because if the root is null, then we don't have a left subtree. And so that's why we return a new binary tree whose root is null, or we return a new binary tree given root left. The right subtree is symmetric, so we just check for null root, check for a right null, and return a new null, or we return the new binary tree with the right node, root right's node as the root, the new root. getData returns the data at the root. So if the root is not null, we return the data, else we return null. And the isLeaf determines if this particular binary tree's root has no leaves. So if root's not null, or if root's null, then it is a leaf, because null is a leaf. Or we check the left and right to be null. If that's true, then this particular binary tree's root node is a leaf. So we want to print out the string, the toString representation, and we're going to use a preorder traversal so that we visit the node, then process the left subtree, and then process the right subtree, and we will indent each of the subtrees to get a nice printout with new lines, and then we output null for empty subtrees. So we actually print out the empty left and right subtrees. So this is an example of what this particular binary tree prints toString would look. So we have the root node is the multiply, this expression tree, and then we indent and we process the left subtree, which would be the plus, and then we process the left subtree, which is the x, and you see that x is a leaf node, so we print out the 2 nulls for the 2 subtrees on x. Then we process the right subtree of the plus. And now we've completed the left subtree of the multiply, so we process the right subtree, and you see we go A, print out the nulls, go to C, and we're done. and it's all nicely indented. So what does that code look like? First off, we have the toString method uses a preorder traversal. We create a string builder to actually do the appends and build up the string, and then we do the preorder traversal of our tree, and then we return the string builder toString, so we have the correct string being returned. And so what is the preorder traversal? Again, we're going to go and first off we're going to get the indentation correct. So we, based upon the depth that we're at, we create that many spaces, and then we visit the root of the node. If it's null, we print out the word null. Else, this is sort of the recursive step. So that node is null is sort of the base case. So now we're going to do a preorder traversal. So we visit the root, which is we get the node toString, we add the /n, and then we traverse to the left, increasing the depth so that we get the right number of indentations. And then once we're done with that traversal, we'll traverse to the right and get the right subtree, and appending everything to the string builder, and then we'll return, and we'll be done. So what's the next function of what's another binary tree? We have a binary search tree. Now, the definition of a binary search tree is similar to a binary tree, except that it has a special caveat on the left and right subtrees. So a set of nodes is a binary search tree if it's empty, or the root node has two subtrees, left and right, such that left and right are binary search trees, and all the values in the left subtree are less than the root node, and all the values in the right subtree are greater than the root node. So the root node will be between the left subtree values and the right subtree values. And here's an example of a binary search tree with the words from a nursery rhyme. So you can see that all the items to the left subtree of lay are less than lay, so they're all alphabetically less, and all the ones to the right of lay are greater than lay, so all they're alphabetically they're greater. So why would we have such a thing? Because we want to have a way of searching through this data to find things, and it allows us a quick search because the depth of the tree is basically log n of the number of items in the tree, so it's a quick search. So what do we do for searching the binary search tree? If the root is null, it's not in the tree, because there's no tree here, we return null. We compare the target to the root data, and if they're equal, we found what we're looking for, and we return the root data. If it's less than the root data, we search to the left subtree. If it's greater, we search the right subtree. So for example, if we're searching for Jill in this tree, the root is not null because it's lay, so we compare Jill to lay, and Jill is less than lay, so we go to the left subtree. Now again, we compare, the root is not null, house is there, so we compare Jill to house. Jill's greater than house, so we do the right subtree. The root's not null, so we compare Jill to Jack. Jill is greater than Jack, so again we go to the right subtree. Root's not null, we compare Jill to killed, and Jill is less than killed, so we go to the left subtree. Again, the root's not null, we compare Jill to kept, and we go to the left subtree, which is now, this time it's null. So the root is null, so Jill is not in this binary search tree. And again, we only had to go basically log n times depth, because the number of comparisons, because we know that it's sorted. So how do we implement a binary search tree? The interface in the book, they define a search tree interface, which allows us to have different implementations of search trees. We have a way of adding the item to a search tree and puts it in the correct place in the tree. We have the contains method, which is similar to the contains from the Java collection. returns true if the target is in the tree, returns false if it's not in the tree. We have a find method, which we just talked about. We return the item if we find it in the tree, or we return null. And then we have a delete, which removes the target from the tree, potentially reordering the tree, depending on what happens, to keep it a binary search tree, or returns null if the target's not in there. And then the remove similarly removes but returns a boolean. This is similar to the queues, offer, and add methods, where you have a way of, or remove and poll, have a way of either returning or not returning the item. So what's the implementation? In this case, our binary search tree, the type of it must be comparable, because we have to be able to compare the target to the data. So what we store must be comparable, so we can get the compare-to method. It extends binary tree, so it's going to be a subclass of binary tree. That's why the binary tree's member variables were protected. The node was protected. And it implements the search tree, so we have to have those methods. And we add 2 more member variables that we have a way of remembering whether the add method returns true or false, and also the return value from the delete method. So what's the find method? Again, we're going to have a public find that takes a target, returns the value. So we have a recursive helper method that allows us to traverse the correct trees if we go left or right, depending on the comparison. So the recursive method is reasonably straightforward, but we needed to add the root node, or the node here, to allow us to traverse the tree. So we first check to see if the node we're at is null. If it is, the thing we're searching for is not in the tree, so we return null. If the node is not null, we compare the target to the data that were at this node. If it's equal, we found the item, so we return local root.data. If it's less than, we're going to search or look for it in the left subtree. If it's greater than, we search for the right subtree. So we're just going to traverse down the tree, either till we get to a null, which means we didn't find it, or we find the data. So let's look at how we can add items to the search tree. And this is a more complicated method, so I've added the runtime stack to help visualize what's going on. And to the right of that, we have the root and the tree structure that we're going to be building. So let's add Jack to the tree. So we call the add method with Jack, and this is a string binary search tree. So the add method calls a recursive helper method to do the work of traversing the tree, finding the right place in the tree, and adding the item to the tree. And we have a return of boolean, so the add return is a boolean, but the root is a node, so the recursive helper method is going to return a node item, and we're going to assign it to root. So I'll show you that next. So the add method calls the recursive helper method, and you can see the runtime stack. We pass in the root, and we then look at this and we say, is the local root null? Yes, it is, because root is null. So we set the add return to true. We have added this item. And we return a new node with Jack in it. So we have the new node, and we're returning that node back to the add method, and the add method then assigns that new node to root. So that's why we have the root pointing to Jack, so that's the root of this tree. And now we can pop the add Jack off the stack, and we're done. And we return the boolean that we set when we created the new node in the recursive helper. So now let's add killed to this tree. So we again call the add item with killed. So we call the recursive method with root with killed. We check to see if the local root is null. It is not. So now we compare the item killed to Jack, and if it's equal, which they are not, we would set the return value, add return to false, because we can't add something that's already in this binary search tree. no duplicates in the binary search trees, and then we return the local root. But since they're not equal, we then compare, see if it's less than, and killed is greater than, so we recursively add to the roots, or the local roots right the item. So we're going to call this method again. So this time the local root is null because Jack's right is null, so we passed in null. So we create a new node, killed, we return it back to here, and so we set Jack's right to this new node, and then we return Jack to the add method, and we assign Jack to the root. And since Jack was the root, we have successfully added the killed to it. So by returning each of the nodes as we pop up the runtime stack, we modify the left or right depending on where we need to add the item in the tree, and then we keep popping up and returning, and eventually we have the modified root is assigned to root, and we remembered whether or not we were successful at adding the item, and we return that boolean. So that's how we do the adds. A little bit complicated, but not too bad. Now if we do deletion, this is where it gets tricky. So first off, if the root is null, the item is not in the tree, so we return null. We were unable to delete the item from the tree because it didn't exist in the tree. If the root is not null, we compare the local root to the item to the local root, and we then, if they're less than, we delete from the left subtree. If it's greater than, we delete from the right subtree. If it's equal, then we remember the data that we're deleting, and then we have to see whether or not the node that we're deleting has any children. If it has no children, we're good. We set the parent root of local to null because we just removed that node from the tree. If it has one child, we make that one child the child of the parent. So we move that one child up one position in the tree. And the tricky bit is if there are two children, we have to find the rightmost node of the left child. Right, this is the rightmost node in the right subtree of the left child. So we got to find the biggest item in the left tree and replace that with our current node with that. Slightly complicated. I hope I can show you that what's going in. And so the delete method is again we have the recursive delete so that we could traverse and modify the tree through the recursion, and then we return the remembered thing that was deleted. If it's not in the tree, we'll return null. If it is deleted, we return the item that was deleted. So here's the recursive method. So again, if the local root is null, it wasn't in the tree, we set the return to null, and we return the local root, because we're going to modify the tree at the bottom or where we get to the right place. So we got to return these nodes in this recursive method. If the node's not null, we do the comparison. So if it's less than, we delete to the left and we return the local root. If it's greater than, we delete to the right and return the local root. Else, we found the item to replace, and so I've written a replacement method, replace node method, which is not in the book, but it has the same code as in the book. I just don't have enough room on this slide to show you what we have to do. So this is where we've got to decide of how to remove the local root's data. So first off, we remember the data that we're removing. We assign it to the deleted return. And so if the local root's left is null, that means we only have a right child, we return that right child. So we're going to do that assignment. So we're basically deleting Jack from the tree and returning killed its right child, so that Jack is now removed, and then the killed will be assigned to what was Jack. Else, we only have a left, so the right is null, so we only have a left, so we return the left. So again, we're removing Jack, we're going to return the is, so that will be assigned to whatever Jack was. Else, we have two children, and now we are searching for the largest node on the right node of the left subtree. So local left right is null, so that means local left is the largest. So in this case, is greater than in. So local left right is null. We set Jack's data to left data. There we go, set to is. Then we set local left to left left by moving up that in. And then we return the local root, which is now modified, so we have gotten rid of Jack, and we return the modified subtree. Now, if the left right is not null, like in this case, we need to find the largest value in the left subtree. So we're going to call find largest on the local root left, and the find largest is going to be starting with the is. So if the parent right is null, in this case it is, so is right is its right is null, we return right data, which would be it, and then we assign parent right to parent right left, which is null, and then we return it, or we recursively continue down. We're going to try to keep going to the right as much as possible until we find a spot that has no more further rights, and then we use that value. So that's the recursive call. We'll keep traversing to the right until we find there is no more rights, and that's the value we use, and that's the thing that we return. That then replaces the local root data. A little bit more complicated, a little trickier, but it does keep the tree a binary search tree, and it is more complicated. And that's all I have. Thank you very much.